Hello everyone. This is part 2 on a series about C++ templates. So in this part we're going to be writing some actual code about templates, and we're going to start with a very simple case, so it would be suitable to someone who's never seen templates before. But we're also going to show some rather complex uses as well, but it's going to be shown in the context of that simple example. So even if you are a user who is comfortable with templates, you might find something new in this. So first we want to find a function which we could sort of improve by making it a template. So a good place to look is in an old C library. So for here example, I have a CMath. And in CMath, if you look at fmax, you can see that it has 4 overloads. So the first takes 2 doubles, the next takes 2 floats, and the third one takes 2 long doubles. There's also a fourth one, but I'm not going to show that one just for simplicity. So we'd like to be able to just have a single max function, right? So this fmax returns which of the 2 values is larger. And ideally, we could not require specific types for this, because 2 types, whatever they are, should be able to determine which among them is the larger of the 2, including for custom types, right? You could have something like 2 dogs, and as long as you have a less than operator defined for your class, you could determine which of the 2 dogs is the max dog. It could be based on which of them is taller or weighs more or is older or whatever you choose. Rather than a max function, though, we are going to look at a function called equals. So here we'd like to compare 2 different objects, which I'll call left-hand side and right-hand side, and it should just return whether these 2 are the same. So the question is, what type do we put here? Right, so this is the name of my variable, left-hand side, because it's on the left-hand side of this equality, and right-hand side. We don't want to do like fmax, where we have a different declaration of a function for each of the different types we expect. We'd like it to work for any type. So this is the basic syntax for a template. So first you say the function that follows is a template, and inside this template there's going to be some type, and I don't know what it is, but the name I'm going to give to this type is just t. And traditionally people use t because it's very succinct, and that t is just shorthand for type. So you could say, well, I'm going to take my two arguments, which can be of any type. In this case they are the same type, and I want to compare them for equality. And what's nice about this is that we can then use our equals with let's say integers, and actually we'll try and make them return true. I can use it for floats. I can use this for doubles. I can use it for unsigned. And these will all work, and all of these particular ones will return true for me, which is fantastic. If you wanted to do it with 2 different types, so here, for example, let's say I have a 1 that's an integer and a 1 that's a float. Here it says that the function template I have doesn't match, because here it expects both of the types to be the same type t, and it says here that the argument types are int and float. What you could do, if you want 2 different types in a template, is you can simply say, well, there's this other type. Typically people use u because it follows after t alphabetically. And you can say, I have 2 types t and u, and so long as they're actually comparable in this way, it still works. So now you can see that this one also works. So this is just to show that you can have a template that has multiple templated types. But for now, we'll just keep it to 1. So what if we have a bit of a funny example here? So here I have 0.42 as a float minus 0.4 as a float, and I want to see if it's equivalent to 0.2 as a float. And I need to change this back to t. And we can see that our bool B actually turns out to be false. And if you're familiar with doing arithmetic with floating point numbers, the problem is that there's some imprecision. Right? So if I open up the immediate window, we can actually check what the result of that is. And you can see it's not quite 0.02. And 0.02 is actually also not represented as 0.02. It's actually represented as slightly off. So the problem is, as a human being, we expect these two values to be equivalent, but to the computer, to the floating point representation, they're not exactly equivalent. So we have a problem here. If you watch the first part, I also lied a little bit. So before, I talked about templates being a form of parametric polymorphism, and that parametric polymorphism means that only the parameters change. Right? So templates are also referred to as parametric polymorphism because the idea is that the parameters change, but the implementation does not. So unfortunately, in this case, we kind of need a different implementation for floating point numbers, because usually you want to say, well, they don't need to be exactly the same as long as they're kind of close enough. So there are a few ways you can go about this, and we'll start with the simplest one, which is something called template specialization. So in template specialization, say I have some template, but it's not going to use any deduce types. So here I'm going to have this implementation of equals specifically for floats. And so it'll take two floats. And here you're going to implement something that takes floating point imprecision into account. Right? So you'll have something where, okay, well, when I subtract these two numbers from each other, what's their relative difference or absolute difference, or however you choose to take account for floating point imprecision. Here I'll just have it return true for now. So this part is up to you to implement. The point here, though, is that we now have one template for the general case, but we also have this template for the specific case of floats. So now if you run this one, where before this one was giving us false, now it's going to give us true. Because rather than using this template for equals, it's using the specialized template that works just for it. So that solves our problem. And you can think, okay, well, we're pretty happy. But then another problem comes along, and you say, okay, well, what if instead of floats, I'm just using doubles? All right, so and then you run this, and you look at your bool, and it's false again. And you're like, okay, well, I can kind of do the same thing. I can say, okay, well, I'll have this other specialized template, and instead of being specialized for floats, it'll be specialized for doubles. And then if you run it, now it's true again because it's using the specialization for double. And then you can say, well, what if I have, a long double, or what if I have some other type that's not one of these two types? So while this sort of helps, and this definitely solves some cases, so in the case of floating point, it wasn't the greatest because there's more than one floating point type, but you might have a specialization for animals, and maybe all animals behave the same except for just a cat, and it's really just the cat. So in that case, it's fine. But we need kind of a way to describe a rule about which template we'd like to use, rather than defining these specialized templates for each of the types that doesn't follow the rules of the general template. So there are two ways to go about this. The first is called tag dispatch, and this is kind of the one that is used more throughout the standard library. It's kind of the older way to go about it, and it's, if you're already familiar, you're more likely to be familiar with tag dispatch than the alternative method if you're aware of these at all. And the second is something called SFINAE, and this stands for substitution failure is not an error. And it's just pronounced SFINAE. So we'll start with tag dispatch. So with tag dispatch, you have one generic template, and then based on some sort of tag, so some sort of identifier, you're going to dispatch the call somewhere else. So we can have an equals floating, which takes a template, and again it does some of the imprecision handling, and we're just having to return true. And then we're going to have an equals for non-floating, so for everything else. And we'd like to be able to choose which of these two that we call from this equals. Actually, it's very important that they have the same name. But conceptually, this is the one for floating, and this is the one for non-floating. All right, and we'd like to pick one of the two. So this is the function that clients will call, and from here, we're going to dispatch it to one of these two. Right, so this is the floating, and this is the non-floating. So how can we do that? So we need some sort of tag, we said. So what we'd like to do is we want to ask some sort of question about this type T that we've been given. So to do that, there's a library called type traits. And inside that library, one of the type traits in particular is called isFloatingPoint. And it takes a type T, and it'll tell you either true or false. And the true or false is contained inside this type def value inside isFloatingPoint. So we can use this isFloatingPoint to then decide whether we want to make one type of tag or another type of tag. So we're also going to use something called conditional. This is also a template. So isFloatingPoint, first of all, is a template. And I'm going to go a bit deeper into this in a moment. And we have this other template called conditional. And you can think of conditional as like just an if condition, right? So if some condition is true, you do one thing. If the condition is false, you do something else. So in this case, we want the condition to be whether or not it's a floating point. And we say, well, if it's a floating point, we'll use this type that's called trueType. And this is a type that's defined inside the language and is typically used for exactly this kind of purpose. And if it's false, we'll use this other type called falseType. And then whether it gives us a true type or a false type, we're going to construct an instance of that type, right? So this is a class. So trueType is a class. So if floating point is true, it's going to give us the trueType class, and we're going to make an instance of it. And if it's not true, we're going to get the falseType class, and we're going to make an instance for it, right? So this is just the constructor for that type. So now we have two different types of tags that tell us whether it's a floating point or whether it's not a floating point. So then in our variation for floating point, we say, well, it also takes a true type as an argument, but we're not even going to give it a name, right? If you had some sort of name, you could use it inside the function, but we're not using it here as one of the arguments we're going to operate on. We're just using it here as a tag to help differentiate it from this other equals. And then similarly, this one will take a false type as an unused argument. And this will help us disambiguate it from this other one. So you have this equals call, which just takes these two arguments. And then based on the type of the argument, we're going to give it a tag. And then we're going to dispatch the call somewhere else. So now we can have an equals that takes two integers. And what we'd like to see is that it ends up over here in the non-floating. Once I fix any little errors I have. I need this to be conditional t. So here we came into the non-floating one when we have integers, which is what we'd like. And then if we have floating point types, we come into the floating point version of equals. So this is tag dispatch. So I'm not going to go into too much detail about what type traits you can check. You could look at the library documentation online to see what else is available. You can also look more at conditional t. I had to do this _t for kind of bizarre reasons. And maybe I'll cover that in some other training, some other tutorial. So isFloatingPoint is a template class. And inside this template class, it has this type def called value, right? So that's going to be true or false. In the same way, conditional is also a template. And inside this template, it has a type def that says whether this ends up being the true condition, which is true type, or the false conditions type, which is false type. I guess I'm explaining it now, and I'm not actually putting it in another tutorial. So it's actually called type. So inside conditional, maybe I can look at it real quick without being too scary. Yeah. So there's a type def called type, and it'll either be the first type or the second type based on whether it's true or false. And we'd like to get that type out of it. So without the _t, the _t is just kind of this convenience version of conditional. So without the _t, you'd have to write, well, I want the value, the type def called type inside conditional. And it's something called a dependent type, which that one I really won't explain as much. You can look into the details, but note that the compiler is not sure whether this type that exists inside conditional is actually a type. So you have to tell it, by the way, this type that I'm getting from conditional is actually the name of a type. So in C++ 14, they added all these kind of convenience functions where you can just go _t, and that's just an alias template. So you can write this _t, and what it does for you is it does exactly what I just showed, right? So it puts type name with conditional, and it gets the type out of it. All right, so back to where we were. So that's tag dispatching. So the second option is SFINAE. Substitution failure is not an error. So I'll stop this, and we'll erase these. And we'd like to do this the other way now. So we'll start by writing what we had before. I suppose I probably should not have deleted all that. I could have just copy-pasted it and altered it a little bit. So here, this is the floating version that handles imprecision. And we'd like to use this first one for non-floating, and this one for floating. So with SFINAE, we're going to use this function called, or this template called enableIf, this templated structure. What enableIf does is it says, if the condition you give me is true, then you're allowed to consider this template when you're trying to figure out which template matches the arguments you've been given. And there are a few different places where you can put this enableIf condition. So I will show you all of them and maybe give you a bit of a reason why you should prefer one over the other. So the first place you can put it is in another template type. So here we're going to make another type name, and we're not going to give it a name. So in the same way that when we use true type and false type, we didn't give them a name because we don't intend to use them, here we're going to have another template type that we don't intend to use. We're just putting it here so we can use this template type to determine whether or not you should be allowed to use this template when you're trying to find one that matches. So here we're going to say we only want to enable if, and again here's this underscore t because we don't want to have to write colon type at the end and type name in front. So we say enable if t, and we want to say, again, is floating point. And this next argument you give is the type that enable if t returns if this condition is true. And you'll see that we're going to use that in other places, but we're not going to use it here because we don't need this type name to have an actual type. So it's just that, enable if t is floating point. And then for the other one, quite simply, you would do the opposite. The problem is, this doesn't actually work for this particular case. The reason why this doesn't work is that the signatures of these two functions are exactly the same. The only thing different is that they have a different default value, right? So you can't have a void foo that takes an int where the default is 1, and then a second foo where the default is 2, because the signature is the same and it can't decide which of these two it should take. So if all you wanted to do was say the only thing you're allowed to compare for equality are things, actually I had this backwards, this is the non-floating point and this is the floating point. If you wanted to say you should only be allowed to call equals on things that are not floating point, then this works just fine. So I could say equals, and here when I'm trying to use it with floating point, it doesn't work. But if I try and use it with integers, did I type that correctly? T, no matching over the function found. For enable if t, oh, maybe I do need a type. Is floating point, oh, because this needs value. Tricky. Okay, no, I don't need the type, I just need that. So this one now works for our integers, and just to show that it actually doesn't work for floats, when I'm getting the proper error message, it does not work for floats. But the problem is we don't just want to enable it for integers only, we'd actually like it for both types. So what we can do is we can move this somewhere else. So another place you can put this, get rid of that. Uncomment this, and put a copy of this over here. So another place you can put it is you can put it in the argument list. And this is going to be another one of these arguments which has a type but not a name because we're not going to actually use it inside of the function. So here you have enable if t, and again we have our is floating point, but this is the not is floating point. T, we get the value, and here we need an actual type, right? So since this is in the argument list, we need it to have an actual type. I should say, by default, if you don't specify a type, the type is void. So when we were using it inside the unnamed type name, you do still need it to have a type, but the default type was fine. In this case, the default type is also fine. It's void. If you want, you could actually write void on your own. But what we're going to do is we're going to say, I want to enable if t, and it's going to be a void pointer if this is true. Right? And we're not going to use this void pointer. And typically you pick a void pointer because it's harder to kind of create a void pointer by mistake. Right? So people don't usually go out of their way to make void pointers. And then similarly, we're going to do the exact same thing here, except we are going to have not floating point. Right? So this is the floating one. So we compile. I didn't actually show you before trying to compile with the two type names that had this different defaults, which I should have, but previously it wouldn't have compiled. Now it does compile, and we can use it for both floating types and non-floating types. And I'll just put these breakpoints here, just run them both. So the first one is the non-floating, and the second one is the floating. So again, before, this SFINAE did not work as a second template type because it deferred only in its default value. Here it doesn't differ in the default value. Like, it has the same default value, but this is different, right? The signature of this is a different class than this one is, right? This is enable if t, which is a templated structure, and its template type is different. So it doesn't have the same signature, right, as this, in the same way that a vector of ints is not the same as a vector of floats, right? So this is not the same type, even though in the end they both end up giving us void pointers. So that's using SFINAE as a different argument type. So the last place you can do it is in the return type. So we'll get rid of not so far, just this part here. So we can actually put it as the return type. And now we need a value that's not void, because this function equals needs to return a Boolean. So if this enable is true, the type it is going to have is bool. Right? So we're going to do the exact same thing over here, and we'll get rid of this. This is the floating. Except I need to remove the exclamation mark there, and you can see it compiles. And if I run it, the first one goes to the integer one, and the second one goes to the floating one. Right? So that is SFINAE. So that's going to be the end of this tutorial. So just to quickly summarize, you can have templates which will take any type, as opposed to needing to specify a different overload for each different type. The basic syntax for a template is not too weird. It's just this template type name t. I should also quickly mention that you are allowed to also use the word class instead of type name. I think people tend to prefer writing type name because it's a bit more generic, because the type you give is not necessarily a class. It could be a primitive type, right? You could have, as in our examples, this one and this integer and this float. They're not actually classes, they're just types. So type name is a bit more generic. But I think if you look at the standard library, they tend to prefer to write class. And I think that mostly comes from the fact that you couldn't use the word type name before. Before you had to write class, and they just kind of stuck with that. So generally you would write type name. If you want to have multiple template parameters, you can also have multiple parameters if you so choose, just like so. Then we talked about how templates are not strictly parametric polymorphism, in that it's not true that they only change their parameter types. You can have template specialization, where you say, well, all of the types will use this one general template, except for this particular type, which I'd like to define a bit differently. Then we saw that there's some problems with template specialization, where you might have several ones that have the same kind of rule. Like you have this category of types that doesn't fit well. So rather than defining a bunch of specializations, we'd like to define some rules, and we have two ways of doing that. Right? The first is with tag dispatch, where we have one function that the client will call, and then we'll look at the type, and then we'll give it some sort of tag, and then there'll be overloads that will take the different tags. So yes, you'll have overloads, but the client never needs to see it. And then the other option was this SFINAE, substitution failure is not an error. And for this one, we use the same kind of rules, but what we do is we turn on and off certain templates based on whether they match these rules, rather than having one function which takes it and then dispatches it to another function call. Right, so this will just say, find me the right function, find me the one that matches these rules. And the part that failure is not an error is that when you're looking through these, since one is turned off, it'll say, well, can I use this one? No, I actually can't, so I failed to use that one. And rather than getting a compiler error, it'll say, well, as long as I can find one template that does match, then I'm happy. And as one last little closing point, when we saw true type and false type, they're actually the base class for all the type traits. So if you look at is floating point, for example, is floating point is actually false for all types, except for the ones that is explicitly defined to be as true, right? So these are template specializations, right? So on our side, we get to use is floating point, and it works for all types, but they actually have to define it as template specialization. So here you can see, yes, float is a floating type, so it's true type. Double is a floating point, so it's also a true type. Long double is also a floating point, so it's also a true type. But all the others are false. So you can see how in the core library, all the types are kind of implemented in terms of this true type and false type for the type traits, I should say. Not everything, just the type traits. You could also do something amusing, like you could pretend that your type is a floating point type, even if it's not. Or maybe you want it to be treated that way for some specific reason, right? So if I have this struct foo, and I don't know what this foo is, but I'd like to say, hey, this foo of mine, it's actually a floating point. So you can say, I want to do a template specialization for is floating point with the type foo, and it inherits from true type. This needs to be a struct. And do they make it public when they do it? No, they don't make it public, so let's make this not public. So here we can now say, well, I made a foo, and I'd like you to treat it as a floating point. And again, this is just an example of template specialization, and maybe you have some sort of reason why you would need your type to be considered as a certain type trait. And you can look at the other type traits, and maybe there are some more interesting cases for it. And that'll be all. Thank you.